All right, in this section, we're going to learn how to use trigonometric substitution to integrate functions. We're going to be working with functions that are algebraic in nature, right? They're going to involve, in particular, one of these radicals. As always, u is a function and a is a constant. The order of subtraction is important, right? If you kind of compare the first one and the last one, they kind of lead us to slightly different substitutions. The idea behind trigonometric substitution is we take a look at this radical and we want to draw a right triangle. And we're going to draw a right triangle. We're going to label one of the sides as A, and one of the sides will be U, and one of the sides will be the radical. And we do it just making sure that it satisfies the Pythagorean theorem, right? We have to make sure that those are actual plausible sides for a right triangle. Now, for example, if we're looking at an expression like the square root of a squared minus u squared, so we have the constant squared minus the function squared, we could label sides of a right triangle as shown here in this figure. When our expression in the radical involves a subtraction, it's always this first guy here, in this case a, that has to be the hypotenuse. What's absolutely critical is that the hypotenuse is labeled correctly. And then it's possible to kind of switch up how you label the two legs. Pythagoras will still be satisfied. Now, if we label the legs of the sides of the right triangle in this way, then we could make a substitution. We could say, let's let u equal a times sine theta. It might seem a little odd, like that. Maybe that just kind of appears out of the blue, especially since our integral doesn't involve the trig function at all at first. And you can sort of see here how we can make that substitution, do a little factoring, write some algebra, and then use Pythagoras, the Pythagorean identity, to kind of get another expression for the radical itself. Now, I almost never kind of just do this by memorizing the substitution that I make. I usually go to, I use SOHCAHTOA. You know, once I've drawn a right triangle, and I know I want to come up with expressions with for trig functions, I use SOHCAHTOA. That's easier. So if we look at this triangle here, you know, for example, if I use the sine part of SOHCAHTOA, I get that sine theta is equal to, opposite over hypotenuse is u over a, and that means that u is equal to a times sine theta. I don't have to remember what kind of substitution to make. You know, this right here, like that doesn't have to come out of the blue. It just is tied directly to the triangle, and using SOHCAHTOA. Similarly, if I use the cosine part of SOHCAHTOA, I get cosine theta equals, let's see, adjacent over hypotenuse is the square root over a, and so that means that the square root of a squared minus u squared is equal to a cosine theta. Right, so we kind of were able to kind of get at both of these substitutions, not by just memorizing that we should let u equal a sine theta. We just use the triangle that we made. And that's generally going to be our approach. This is going to be kind of the easiest, simplest way to think about this. So we're going to do an example. We're going to do a bunch of examples, actually. So in example 423, we want to integrate dx over x squared times the square root 9 minus x squared. So my initial focus immediately is just on this radical, that radical expression. I know that I need a substitution. I'm going to need one for the radical. I'm going to use the radical to help me make my triangle. And then I'm going to need to have substitutions for the radical, for x squared, and for dx, right? Because we know that making a substitution is all about accounting. I have to have everything accounted for. So let's see, over here on the side, I'm going to just draw this right triangle. Here's my angle theta. And I'm going to label the sides like this. I know that because it's a subtraction, I have to label the hypotenuse as 3. 9 is a squared, so I'm labeling the hypotenuse as 3. The other two sides will be x and the radical itself. I'm going to put the radical itself on the bottom. And now, using the sine function of SOHCAHTOA, I know that sine theta is x over 3, and so x is 3 sine theta. Now, before I get an expression for the radical, I'm going to use this and I'm going to get two other things. One, I'm going to find dx, right? Dx, the derivative of 3 sine theta is 3 cosine theta. So dx is 3 cosine theta d theta. And we know that x squared, if I just square the expression, x equals 3 sine theta, we know that x squared is 9 sine squared theta. Alright, so I've got my substitution for x squared, I've got my substitution for dx. Now I'm going to get a substitution for the radical itself, and to do that I'm going to use the cosine part. I'm using the cosine part because that'll get me an expression for the radical and the constant. And that'll be a lot easier than having an expression with the radical and x. So the cosine part gives me cosine theta equals the radical over 3. And so the radical is equal to 3 cosine theta. So there's my last thing that I need in order to make my substitution. Let's note, that if you look at the integral at first, right, as it's given, dx over x squared times the square root of 9 minus x squared, we don't really have a great, path forward for that integral. Like, the techniques we already know will not really work well for us here. There's not a u substitution that jumps out at me. But using the trigonometric substitution, when I make this substitution, let's see, on top we have dx, so that's 3 cosine theta d theta. On the bottom, x squared is 9 sine squared theta, and then the radical is 3 cosine theta. The whole idea behind trigonometric substitution is that the trigonometric integral we end up with when we make the substitution is one that we know how to do, or at least more manageable than the one we started with. We could do some simplifying. Let's cancel the 3's. We'll cancel the cosine theta. I'm going to pull out this factor of 1/9. And then a sine squared in the bottom, well, that's cosecant squared theta. D theta. We know the integral of cosecant squared, that's a negative cotan squared, so this is minus 1/9 cotan squared theta plus a constant. Now we are almost done, but we should remember we started out with an integral with x's. The answer should not be an expression, a function with thetas. So we have to go make our substitution back, and I just, use SOHCAHTOA again. So cotan is, let's see, if tangent is opposite over adjacent, cotan is adjacent over opposite. So this is minus 1/9 times cotan, I wrote cotan squared. Let me just acknowledge my error. The integral of cosecant squared is negative cotangent, not cotan squared. So cotan is adjacent over opposite, so that's the radical, 9 minus x squared over x. And I'm just going to simplify this a little bit. So minus the fraction radical 9 minus x squared over 9x plus a constant. Okay, Let's try another one. This integral looks fairly simple in terms of it doesn't look like there's a whole lot involved. Not so simple in that we don't already have like one of our other techniques doesn't really work. There's not an obvious u substitution to make. But I see that I've got this radical involved. Moreover, I could see that radical as a u squared plus a squared, right? 4x squared is the square of 2x. And of course, 1 squared is 1. Now, when we have a sum inside, when we're adding inside that radical, then it's the radical itself that has to be the hypotenuse. So my radical, my hypotenuse is 4x squared plus 1 in the square root. And then my two legs, one of them will be 1 and one will be 2x. I'm going to throw 2x on the vertical side and 1 on the bottom. It can work either way. You know, how you label the two legs is not as crucial as just making sure that we get that hypotenuse right. As long as Pythagoras is satisfied, this technique should produce a valid result. So let's do some of the work for the substitution here. We need an expression for the radical for sure. We could see that. But we also need to get an expression for x. And the reason we have to make sure we can get an expression for x is because we need an expression for dx, right? We have to make that substitution as well. So I'm going to start by using the TOA part, the tangent part of SOHCAHTOA. We know that tan theta is 2x over 1. So tan theta is 2x, and that means that x is 1/2 tan theta, and so dx is 1/2 secant squared theta d theta. So there is one thing that we need a substitute for. And now to get an expression for the radical, I really, in this case, it's like before, it's going to be much easier on us if we get an expression using the radical and the constant side. So I'm going to use cosine. Cosine theta is 1 over the radical. And that means that the radical itself is going to be 1 over cosine, or secant. So we've got the things we need substitutions for. So now let's make our substitutions. On top we have dx, that is 1/2 secant squared theta d theta. On the bottom we have the radical, that is secant theta. We're going to pull out that factor of 1/2. Reduce this. We could cancel one of the factors of secant. So now we have 1/2 times the integral of secant theta d theta. The integral of secant theta is one that we know, or at least one that we know is on that sheet of integrals that we're not really maybe expected to memorize. The integral of secant theta is ln of absolute value secant plus tan. Plus a constant. And then just like before, and this is one thing we're generally going to need to remember, you know, they give us an integral with x's. The answer is not going to be a function with thetas. So we have to go back to the, I always go back to the triangle to make our substitutions back to x's. Secant is the reciprocal of cosine, so that'll be the square root for x, the square root of 4x squared plus 1. And then tangent, using SOHCAHTOA, is 2x over 1, so tangent is 2x. And then plus a constant. All right, let's try another. This integral, I guess, kind of similar to the last one. We have a sum of squares there, and it's raised to the 3/2 power. Of course, that means we just have a square root that's being cubed. So I think the type of substitution that we're going to make is the same. We'll see what the integral ends up looking like with trig functions. So we have a sum inside the radical. That means that the radical has to be the hypotenuse. I'm going to label the opposite side x, and the bottom will be 1. So, all right, using cosine, we get cosine theta is 1 over the square root of x squared plus 1. And so that means that the radical is equal to secant theta. So there's one substitution that we need. Using the TOA part, the tangent part of SOHCAHTOA, tan theta is x over 1, or just x. And so that means that dx is secant squared theta, d theta. And that is the other substitution that we needed. So I think we have everything we need to make this substitution. So now on top, let's rewrite this integral. Dx is secant squared theta d theta. On the bottom, we have the radical cubed, so that's secant cubed theta. We can do some reducing, like we did before, right? So the secant squared is gone, and we're just left with secant in the bottom. 1 over secant is cosine. So we have the integral of cosine theta d theta. We know the integral of cosine. The integral of cosine is sine. So this is sine theta plus a constant. Going back to the triangle, sine theta, opposite over hypotenuse, that's x over the square root of x squared plus 1. Plus a constant. All right, let's do another one. In this case, our next example is a definite integral. And, we're already familiar with, when you're using a u substitution on a definite integral, that you can change the limits of integration. And I find that to be pretty convenient here as well when we're doing a trigonometric substitution. So let's have a go at this one. Again, we're looking at the expression in the radical to kind of guide our substitution. And this starts with drawing and labeling a right triangle. So there's our angle theta. It's a subtraction. So it's the first expression, the first term that'll be the hypotenuse, in this case x. And now the other two sides, one will be the radical and one will be the square root of 3, right? Because 3 is a squared. I'm going to label the bottom side as root 3 and the vertical side as the radical. Now let's see what we got. We need to get an expression for the radical. We need an expression for x, but it might actually be a bit quicker to realize that we could actually directly get an expression for that fraction using the sine function. SOHCAHTOA tells us that sine theta is the square root of x squared minus 3 over x. So there's one substitution that we need. Now, because we need dx, we do still need to get a substitution or an expression for x so that we can get the substitution for dx. So I'll use the cosine function because that uses x and just the constant side. So SOHCAHTOA tells us that cosine theta is √3 over x. And that means that secant theta is x over √3. And if we multiply both sides by √3, we get x is √3 times secant theta. And so dx is √3 times the derivative of secant is secant tan. So secant theta, tan theta, d theta. So there is our other substitution. All right, so now this integral turns into, let's see, that fraction initially, that's sine theta, and then dx is √3 secant theta, tan theta, d theta. The only thing we don't have yet are the limits, right? So we need to figure out what are our theta limits. And that is another reason why we want to have an expression for x. We're going to use that expression for x, the equation with x and theta, to find our limits. So we know that, let's see, when x is equal to √3, that's our lower limit, that gives us the equation then. Again, I'm just using this substitution, that expression for x, rather, up here. So √3 equals √3 secant theta. And that means that secant theta has to be equal to 1, which means cosine is equal to 1. They're reciprocals. And cosine is 1. If we look at the unit circle, we could see cosine is the x coordinate. So that happens at 0 radians. And then for the other limit, x equals 2 gives us the equation 2 equals √3 times secant theta. That means that secant theta is 2 over √3, which means that cosine theta is √3 over 2. Again, if we look at the unit circle, √3 over 2, cosine is √3 over 2 at pi over 6 radians. So our new limits, our theta limits, are from 0 to pi over 6. All right, let's rewrite this. Let's see how we can integrate this this integral. It'll surprise no one to see that I'm going to yank out that factor of √3. And then we have sine theta times secant theta, and then times tangent. So sine theta is, well, secant theta is 1 over cosine. So this is really like sine theta over cosine theta times tan theta. But sine over cosine is, this is equal to tan theta, right? So really what we have is tan squared. Now, tan squared is not one of the like kind of simple trig integrals that we just know or have a formula for, but we have a technique for. In the last section, we saw that when we're integrating powers of tangent, if we just have even positive powers on tangent, let's convert it to secants. So Pythagoras tells us that tan squared theta is secant squared theta minus 1. We derived that probably a few times in the last section, so you can go back and review that if you need to, just using that fundamental kind of Pythagorean identity of sine squared plus cosine squared equals 1. We can rewrite this integral in that way. And now we know how to integrate this. We know the integral of secant squared is tangent. We know how to integrate 1 with respect to theta. That's just theta. So when we integrate, we get tan theta minus theta from 0 to pi over 6. And we don't have to go back to x's now because we converted our limits to theta limits. So we don't have to worry about that. Now we're ready to just kind of plug in those limits. So if we plug in pi over 6, tan pi over 6 minus pi over 6 minus plugging in 0. Now tangent of 0 is 0, so that means really this whole second expression zeroes out. Tangent of pi over 6. Tangent is sine over cosine, and if I look at pi over 6, sine is 1/2. Cosine is root 3 over 2. So when you divide, you get 1/2 times 2 over root 3 minus pi over 6. You can cancel that factor, common factor of 2 here. And now if we distribute this factor of root 3, right, back into the parentheses. In the first term, it'll cancel that 1 over root 3, so we get 1, we get 1 minus root 3 times pi over 6. And there it is, the exact result. And if you like, you can approximate and we get 0.0931. I do want to point out before we move on to the next example that, you know, because this was a definite integral, we know that we could substitute, get new limits, get theta limits. If it were an indefinite integral and we found ourselves needing to go back to our x's, right, the expressions with x's, we use SOHCAHTOA like we did in the last ones for tan theta, and then for theta, getting an expression for the actual angle theta would involve an inverse trig function, and probably easiest done either just by going back to this expression here, right? You could figure out, or actually maybe this expression here, right? If cosine theta is root 3 over x, then that means that theta is arc cosine of root 3 over x. Okay. Let's try another one. So as the introduction to this problem states, we're going to need to complete the square here. I can tell, the way I can tell that we need to complete the square is that I have not just an x squared term, but also an x term. So this is not just a difference of squares here. When we use this trigonometric substitution, it's because we're looking at something that could involve a radical where inside we have a sum or difference of squares. And So we kind of need to get this in that type of form. So let's see what happens when we complete the square on this expression. So we have x squared minus 4x is the expression we have. And I know that if I want to complete the square, I'm going to do so by adding the square of half the middle coefficient, half that coefficient on x. So we're going to square negative 2 and add that. I can't just add that without compensating, so I have to subtract it off as well. And then those first three terms, that's a perfect square. That's x minus 2 squared minus, and then negative 2 squared is 4. So there's the expression equivalent to x squared minus 4x. So now I'm going to rewrite this integral. And in addition to substituting x minus 2 squared minus 4 in for that expression with x's, I'm also going to take care of the fact that this 3/2 power means we're cubing a square root. All right. So now that we've completed the square, we can see this does sort of fit that form that we need to be able to draw a right triangle. It's a subtraction inside that subtraction right there, and so the beginning, or the hypotenuse, when we start this out, it's the hypotenuse that has to be labeled as x minus 2. Alright, so there's x minus 2 on the hypotenuse. And then between the two other sides, one of them will be 2, and then the other will be the radical itself. I'm going to put 2 on the bottom. I'll put the radical on the other side. And just for the sake of making it easier to write, I'm going to write it as x squared minus 4x instead of the other expression. But you could write it either way. Alright, so now, we've done all of this, this setup work. We have our triangle drawn. We need to get expressions to make our substitutions. We need an expression for the radical, for sure. We also need an expression for x so that we can get a substitution for dx. If I'm getting an expression for the radical, I'm going to use tangent, because tangent uses the radical side and the constant side, and that makes it a little bit easier. So TOA tells us tan theta is equal to the square root of x squared minus 4x over 2. And so the radical is equal to 2 times tan theta. So that one's all set. We need an expression for x. So to get an expression for x, I'm going to use the hypotenuse and the constant side. So that'll be cosine. Cosine is 2 over x minus 2. That means that secant theta is equal to x minus 2 over 2. And if we multiply both sides by 2, we get x minus 2 is equal to 2 secant theta. And then we just add 2 to both sides. Now we can get dx. So that'll be a 2 secant theta tan theta d theta, right? The derivative of 2 is 0, so that constant term drops off when we find dx. And I think we have everything we need to make the substitutions. So here it is again written algebraically as an algebraic function. And again, I'm just using the shortened version of the radical. We know that this is, let's see, substituting for dx, we get 2 secant theta tan theta d theta all over. The square root is 2 tan theta, and we're cubing that. I'm going to do a little bit of algebra to rewrite this to help us simplify. Cubing the bottom gives us 8 tan cubed. And now we can do some canceling. So 2 goes into 8 4 times. That tangent cancels, and we have a tan squared in the bottom. I'm going to pull that 4 out. It's a factor of 1/4. And then up top we have secant theta over tan squared. Alright, so now we've got this simplified trigonometric integral. So we need to kind of rewrite this so that we can kind of have a path forward. Think about those trig integrals we learned about in the last section. And there's nothing that really jumps out at me right now as far as the substitution that'll work. So what I'm going to do is just rewrite things in terms of sines and cosines and then go from there. So secant is 1 over cosine. And then tangent is sine over cosine. And since it's in the bottom, dividing by sine over cosine means we're multiplying by cosine over sine, but it's squared. So that'll be a cosine squared theta over sine squared theta. We can cancel out the cosine. And we have a couple of ways we could proceed from here. The way that I'm going to rewrite this is that I'm going to see this as a cosine over sine times a 1 over sine. Right? That accounts for both factors of sine in the bottom and the single factor of cosine on top. So that factor of 1 over sine is cosecant times cosine over sine is cotan. And cosecant cotan is an integral, we know. I'm going to go back up. I'm going to scroll up a little bit where I have a bit more space. The integral of cosecant cotan is a negative cosecant, so this is negative 1/4 cosecant theta plus a constant. Now we're not quite done. Again, we started with an integral with x's. We want a result that is a function of x, not a function of theta. So cosecant is the reciprocal of sine. I'm going to go back up here to the triangle. SOHCAHTOA tells us that sine theta is the radical over x minus 2. So cosecant will be the reciprocal of that. This will be x minus 2 divided by the radical. X minus 2 divided by the radical. And then I'm just going to simplify a little bit. I'm going to write it as a single fraction, and then on the bottom I have 4 times the radical x squared minus 4x. Up top I'm going to distribute that minus, so just flip the order of subtraction, so it'll be a 2 minus x. Okay, so let's do another one. This one's a little bit different than the others. The radical doesn't really jump out at us because it doesn't look like we have a 1/2 power. They've given us an integer power, but we can always rewrite that in terms of raising a radical to the appropriate power. So if we have x squared plus 1 squared, I can see that as the square root of x squared plus 1 raised to the 4th power. So there's our radical. We'll use that radical to help us draw this triangle and make the correct substitution. It's a sum. We're adding inside that radical, so that means it's the radical itself that is the hypotenuse. And then the legs will be x and 1. I'm going to go ahead and label the vertical leg as x and the bottom leg as 1. And we need substitutions. We need to figure out what x is so we can get a substitution for dx. And so that's easiest by using the tangent function. We know that tan theta is equal to x over 1, or just x. And so if we take the derivative, dx is equal to secant squared theta d theta. So there's one substitution. And then we need an expression for the radical itself. So I'm going to use the function that uses the hypotenuse and the constant side, the bottom leg there, and that's cosine. Cosine theta is equal to 1 over the square root of x squared plus 1. And that means that the radical is equal to secant theta. Okay, now let's make our substitutions. Rewrite this. Up top we've got dx, that is secant squared theta d theta. On the bottom we have the radical squared, so that'll be secant to the 4th of theta. Do some reducing. Secant squared cancels completely. I'm left with a secant squared in the bottom. So 1 over secant squared is equal to cosine squared. And thinking back to the last section on trig integrals, if I have an even positive power of cosine, what I'm going to do is use the half angle identity to rewrite this. So this is 1 plus cosine 2 theta over 2. I'm going to yank out the 1/2. And actually, maybe what I'll do is just split up the fraction over that addition. And then split up the integral over that addition. So we have the integral of 1/2 d theta plus 1/2 times the integral cosine 2 theta d theta. Now the integral of 1/2 d theta we know how to do. That'll just be 1/2 theta. For the integral of cosine 2 theta, I think we also basically know how to do that. That can be done by letting u equal 2 theta, so that du is 2 d theta. We need a factor of 2. And we'll compensate with the factor 1/2 outside. Now this is the integral of cosine u. And we know the integral of cosine. The integral of cosine is sine. So this will look like, let's integrate them both in one go here. The integral of 1/2 d theta is 1/2 theta plus, let's see, 1/4 times, this will be sine 2 theta plus a constant. Now this is an indefinite integral, so like we have to go back to x's, right? We want to function with x's. We have a couple of additional challenges in doing that this time. We always use our triangle to get that expression. Because our integral, the result involves just theta and not trig, not just a trig function of theta, but theta itself, we're going to need to use an inverse trig function to get an expression for this first term of 1/2 theta. But also, this result here that we got is sine of 2 theta. we don't have a triangle with an angle of 2 theta. We have a triangle with an angle of theta. So I got to convert that second term into an expression that just uses theta. And we can do that using the double angle formula for sine. Sine of 2 theta is 2 sine theta cosine theta. And now I think we're ready to get to x's. So let's go back up here. We know that tan theta is equal to x. And so that means that theta is arctan of x. So that's what we're going to use for the first expression. So we have 1/2 arctan x. One quarter times 2 is 1/2. Sine theta is x over the radical, and cosine theta is 1 over the radical. I'm just using SOHCAHTOA with that right triangle that we have. Plus a constant. And now we'll simplify. You get 1/2 arctan x plus, and then this fraction will be x over 2 times x squared plus 1 plus a constant. All right, one last example. We have some special integration formulas, I mean, these formulas are really all derived from using trigonometric substitution. There's no need to memorize these formulas. Anytime you might want to reach for one of these formulas, it's something where you could do it using a trigonometric substitution. We're going to do an example here, and it'll be one involving arc length. So we want to find the length of the graph of f of x equals 1/2 x squared from 0 to 1. So if we think back to the last chapter, we know arc length is given by this integral formula. And so they gave us our function, so we're going to find f prime of x, and that's pretty immediate, just using the power rule. F prime of x is x, and so that means that 1 plus the square of f prime is 1 plus x squared. And that means that to solve this problem, to find the arc length, we want to integrate from 0 to 1 the square root of 1 plus x squared. Now, you could use the third formula, right? We have a sum of squares inside a square root. But our techniques will work, right? The techniques that we've been learning this section will work just fine. So I'm going to go ahead and do this by making the trigonometric substitution. You could do this by fitting it to the formula that's in the formula 3 there, if you want. So if we're going to use trigonometric substitution here, we've got this sum of squares in the radical, so I'm going to draw the triangle. We know that the hypotenuse has to be the radical. I'm going to label the vertical side as x and the bottom side as 1. Using SOHCAHTOA, we know x is tan theta, and so dx is secant squared theta d theta. We also know that cosine theta is 1 over the radical, so the radical itself is secant theta. So this is what we need for our substitutions. And here I neglected to write dx on this original integral there. Okay, now this is a definite integral, so I'm going to just find some new limits. I'm going to use x equals tan theta to convert the limits of 0 and 1 to theta limits. So if x is equal to 0, then 0 is equal to tan theta, and tangent is equal to 0 when theta is equal to 0, so that x equals 0 limit converts to a theta equals 0 limit. And then x equals 1 means that 1 is equal to tan theta, and tangent is 1 at pi over 4. So this is theta equals pi over 4. So let's rewrite this integral. This is going to become the integral from 0 to pi over 4 of secant theta times secant squared theta d theta. Simplifying, we get the integral from 0 to pi over 4 of secant cubed theta d theta. So this is a good opportunity to have a nice callback to the last section. This particular integral can be a little tricky, but we already worked it out in the section on trig integrals. It was example, let me go back and find it. Oh, you know what? It was not in the last section. I think it was this section on integration by parts. Here it is, example 411. So we integrated this function, and we got this result. So now we're just going to reap the fruits of our labor. We're not going to go redo this whole thing. We're just going to use this result. So this is 1/2 secant theta tan theta plus 1/2 ln of absolute secant theta plus tan theta from 0 to pi over 4. And now we can plug in our limits. I'm gonna, I think, just take out these common factor, this common factor of 1/2. Bring that outside. Plugging in pi over 4. Now when we plug in 0, I'm going to leave, you can kind of work out the actual details here, but tangent of 0 is equal to 0. So if we plug in theta equals 0, that term definitely zeroes out because there's a factor of 0. Secant of 0 is equal to 1, and tangent of 0 is equal to 0. So this becomes ln of 1, and ln of 1 is 0. So the whole thing will zero out when you let theta equal 0. Secant pi over 4 is the reciprocal of cosine pi over 4, and so the reciprocal of root 2 over 2 is root 2. Tangent of pi over 4 is 1. So this becomes 1/2 times root 2 plus ln of 1 plus root 2. There it is as an exact value, and we can also get an approximation. We get 1.148.